If you can't see the 5 numbers, you might be considered red-green colorblind, which strangely enough has to do with your ability to process visible light, or the colors of the rainbow. Color blindness tends to affect more males than it does females. There are 3 main types, each of them slightly different in how someone perceives color, but what it has in common is, typically the reds and greens are confused, and it's muddled all into one color that kind of looks like yellow. Someone with normal color vision can perceive the whole entire spectrum of the color wheel, whereas anyone who's colorblind finds it hard to distinguish red and green. Those 2 tones get blended together. The 3 primary colors of light are red, green, and blue. The reason why that shirt appears red is because whatever materials and pigments make up that shirt, they're absorbing every single color except for red. Red is being reflected back into your eyes, and that's why you perceive it as the color red. These are the 3 primary colors again. So red, something that appears red is because it's reflecting the color red, so then your brain perceives it as red. You perceive green whenever you're receiving green wavelengths, and any blue object appears blue because blue is being reflected into your eyes, and then you understand it or you perceive it as blue. You can mix these primary colors as well, and it lends you the other colors of light. So red and blue will give you magenta. Red and green gives you yellow. Green and blue gives you cyan. And if you mix all 3, you get white. Now if you tone these all down, guess what you have? You have black, or darkness. So black is the absence of light, or the absorption of all light. If you've ever heard anyone say, don't run outside on a hot sunny day wearing a black shirt, they're probably right, and that's because black is the absence of light, or the absorption of all light. So black materials or black pigments tend to absorb a lot of heat and light, which is why it causes you to overheat. Color vision is the ability to perceive visible light, which is a very narrow band on the electromagnetic spectrum. EM waves are forms of light, most of which you can't see. The only band that you could see is visible light, but what they all have in common is they all move at the speed of light, which is 3 times 10 to the 8th, or 300 million meters per second. EM waves are ordered by increasing wavelength, or from low to high energy. Or another way to think about it is from least harmful waves to the most harmful waves. So from left to right, the least harmful is radio, microwave, infrared, visible light, UV, X-rays, and the most harmful, gamma rays. Animals have a much wider range of vision than humans. It's speculated that certain animals like dogs, cats, birds, bees, and reindeer can detect UV light, whereas rats and snakes can pick up infrared radiation. You should probably understand that wavelength and frequency are inversely related, meaning if one of them gets bigger, the other one decreases. So as you can see in the illustration in the center, a wavelength is defined as the top of each wave from crest to crest. So if you were to compare red and blue light, red has longer wavelengths, but it also has lower energy or lower frequency. Meanwhile, blue has shorter wavelengths, but higher frequency or higher energy. Here's a visual that can illustrate how wavelength and frequency are inversely related. If I move this thing up and down with no effort at all, you can see how the wavelengths are pretty long, and this thing has a low frequency. So it's long wavelength, low frequency. But if now I exert a lot more effort or energy, I put more energy into this, the frequency goes up. So this is high frequency, and if you look carefully, the wavelengths are a lot shorter. So this is high frequency, short wavelengths, which means they're inversely related. Frequency is measured in units of hertz, or Hz, which is waves per second. And you can count the number of waves that pass through in a single second. I'll put my mouse here and we'll count the rhythm or the pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 complete waves or 10 complete revolutions in 10 seconds, which comes out to 1 wave per second. Now the other thing that we'll keep track of is the wavelength. So the wavelength from this crest to this crest is about 6 centimeters. So it's a 6 centimeter wavelength for a frequency of 1 hertz. This time I've increased the frequency, I've tripled it, so now it's 3 hertz or 3 waves per second, and we can actually count that rhythm. So this is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And we'll pause it there. We'll measure the wavelength. So from this crest to this crest, that's about 2 centimeters. So for a frequency of 3 hertz, you have a wavelength of 2 centimeters. As you can see, wavelength and frequency are inversely related, which means if one of them gets bigger, the other one gets smaller. And when they're multiplied together, they produce a constant which later on we'll learn is the speed of light. So in trial 1, you could see I had a wavelength of 6 and a frequency of 1. 6 times 1 gets you 6. In trial 2, I had a wavelength of 2 and a frequency of 3. And when I multiply 2 times 3, I also get 6. So just keep in mind for now that wavelength times frequency produces a constant, which later on is the speed of light. Reading this chart is really easy. Just keep track of the wavelength and the frequency. So we'll start with radio waves. Radio waves are measured at 1,000 meters, so really big wavelengths. And if you go straight down, let's draw a line straight down, it's around 10 to the 4th hertz. Okay, I mean 10 to the 4th, relatively speaking, is a pretty large number. That's about 10,000 waves per second. But let's move across the spectrum. Let's go to microwaves. So 10 to the minus 2 means it's a smaller wavelength now, a shorter wavelength. And if I draw a line straight down, that's around 10 to the 10th for the frequency. So the frequency has now increased, right? So you've gone from 10 to the 4th to 10 to the 10th. Now I'm going to move all the way over on the far end of the spectrum, and let's look at gamma rays. So 10 to the minus 12th is the wavelength, so really small wavelengths. And now look at the frequency. The frequency is 10 to the 20th. It's massive, right? It's huge. So that's a really short wavelength and a really high frequency, really energetic. So gamma rays are the most harmful because they're also highest in frequency. Let's do a wavelength times frequency equals speed of light calculation. So this is number 22 and 23. They go together. The equation is given. Okay, and the problem is asking what is the frequency of a wave that has a wavelength of 2.3 times 10 to the minus 2 meters. And in problem number 23, you're asked to identify the wave. So obviously I'm going to look at my equations over here. So wavelength times frequency equals c, which stands for the speed of light. And you'll see it represented like this too with Greek letters. So lambda times nu equals c. And the reason why speed of light is c is because it stands for celeritas, which is Latin for swiftness. Okay, I'm going to use these symbols. So lambda times nu equals c. And I look at my problem again. I'm going to see what it's asking. It's asking what is the frequency. So that means I'm going to go to my equation. I'm going to circle this symbol here, nu, which stands for frequency. Now I'm going to isolate it. So this is algebra, just simple algebra. Now I'm going to plug in for c, the speed of light, 3 times 10 to the 8th meters per second, divided by the given wavelength, which is 2.3 times 10 to the minus 2 meters. Meters would cancel out. I'm going to use my calculator. I get 1.3 times 10 to the 10th hertz, or waves per second. Now, in problem 23, I'm going to use this chart. Okay, so my given wavelength was around 10 to the minus 2. So you see how I drew that blue dot on there? And the frequency that we just solved for was 10 to the 10th. I'm going to draw a line connecting those two dots, and it looks like it crosses the boundary of microwave. So this wave is a microwave. Wavelength times frequency is equal to a constant, which is the speed of light. The speed of light is 3 times 10 to the 8 meters per second, but I'm just going to round and call it 10 to the 8. Now I'm going to draw a line connecting wavelength and frequency. So I'm going to write down their numbers. So for wavelength, if you look on the chart carefully, it's 10 to the 4th, and frequency is 10 to the 4th. And when you multiply those two numbers, you get 10 to the 8. So that checks out. That proves that it's a constant so far. Let's go to microwaves. Let's look at their numbers, and let's draw a line. So this is 10 to the minus 2 for wavelength, and the frequency is 10 to the 10th. I know it's really small, but when you multiply those numbers, you get 10 to the 8th. Wow, it's a constant. And now let's look at X-rays. So for X-rays, the wavelength is 10 to the minus 10. The frequency is 10 to the positive 18. And when you multiply, you get 10 to the 8. So that checks out. So far, so good. And now let's check gamma rays. Let's draw a line straight down connecting those two numbers. So the wavelength is 10 to the minus 12th. Frequency 10 to the 20th. And the constant is 10 to the 8th. So again, wavelength times frequency is a constant. Constant is the speed of light. And that's because wavelength and frequency are inversely related. Radio waves are often underappreciated. They carry information at the speed of light. You can't see them, but currently there's a chaos of radio and TV waves traveling outside of your window right now. These waves are sending and receiving information to cell phones and TVs and radios belonging to the people who live all around you. So the next time you stream a music video, you can thank the electromagnetic spectrum for giving you entertainment practically from thin air. Thanks for watching my lesson on this topic, and I'll see you next time on Wind Chemistry.